Okay, in this section, we're just going to be reviewing our basic integration rules, and for the most part, these rules you've already seen in previous chapters. The only new feature is that we're going to be doing a little bit more complicated u-substitution, which I put in the red, the bottom part here. Okay, but these 5 rules are things that we've been playing with for definite integrals. If we're trying to find the integral of 2 functions being added together, then we could integrate the first function and we can add and subtract the integral of the second function. If we had a constant times a function, that constant can just come right out and we can integrate a constant times that integral. And that's a lot of these rules are very similar with derivatives. If we integrated it over a single point, then there would be no area underneath the curve. The dx effectively would be 0, and we have a result of 0. This one is kind of a mysterious one, but if you think about this negative negating the dx, and it's reversing the direction that we're integrating. And so if I switch the order, that makes this dx become positive. And so by factoring that negative in, removing the minus dx flips the integration. And this is a really powerful result, because if we integrate, say, from sum a here and up to sum b, we can integrate from a to c. So we can integrate just here, and then we can integrate from c to b if you want. And that may make it easier, because maybe in this region, the function is a nice triangle, and maybe in this region, some weird function, and we're trying to find the area underneath the curve. It may behoove us to actually figure out this area here first, and then calculate that area. But really the crux of this particular section in your homework is dealing with the u-substitution. So this is the case where our function, our integrand, this is our integrand, but one of the functions in the integrand has guts to it. So in this case, the guts to it, I'm giving the letter G for guts. And if we were to let u equal to g of x, then we could differentiate by the chain rule. We find du is equal to dx. And so I don't have my stylus here right now, but I have u is equal to g of x. Then if I were to differentiate both sides with respect to x, then I'd find du is equal to g prime of x dx. And then I could transform the integrand and the infinitesimal area piece du. And notice the bounds of integration have been changed as well. So if x is equal to a and u is equal to g of x, and if I plugged in x equal to a, then u would equal g of a. So we can transform the entire integration result. That often can make the integral pretty easy. Now, the next 2 examples that I've shown on here is looking at more complicated u-substitution. I'm going to change that to a 3. So 3x squared up here, or x squared plus 9. So I want to walk through an example of how we could, say, work through a complicated rational function of trying to find the integrand. And here, the first thing I'm going to do is I'm actually going to do a polynomial division. And when I do that, first factor out that 3, but here, that polynomial of x squared over x squared plus 9 can be written as 1 minus 9 over x squared plus 9. So that means if I use my very first rule on the previous page, this rule, I'm looking at that I have the difference of 2 functions. I'm going to integrate the first piece, which is the integral of 1. So that's x. X times 3 is 3x. And I'm going to factor out that 9 in the second integral of minus 27 times that integral. Now we recognize 1 over x squared plus 9 looks like something involving an arctan. And I just factored out a 9 in the denominator to write that second integral, this expression. So I'm starting to see this looks like an arctan of the quantity x over 3. We actually do our first u-substitution here, only on the second interval, because the first piece has already been done. And so we let u equal x over 3. Therefore, by the chain rule, du is equal to 1/3 dx. And therefore, I can plug in dx equal to 3 du. And we plug in, factor out that extra 3. Again, that's using this constant multiple rule number 2. And once we have that, we have 3x minus 9 du over u squared plus 1. And we recognize this integral, the antiderivative, is arctan of u. And then we can substitute back in, and we have our final result. Here. So this is a little bit more complicated steps to be able to find that antiderivative. But I can go over to Desmos if I want. I can type in this function and then take the derivative and see if that equals to that function as well. And let's do that right now. So I'm going to go over to Desmos. So take the second to load up. And we have an arbitrary constant. I'm just going to neglect the arbitrary constant because I'm checking to see if the derivative of my expression equals to the integrand of the original integral. So we have 3x minus, and I think it was 3 arctan, or minus 9 arctan of x over 3. So minus 9 arctan of x over 3. You know, and I don't really care about the graph of this function. What I do care about is the derivative. And now what I'm going to do, I'm going to see if the graph of the derivative is equal to the integrand's graph. So 3x squared all over x squared plus 9. And we see, look, they're right on top of each other. That means this is an an antiderivative of this particular integral. Okay, we can do the same thing here. Okay, this looks really complicated, but the key is to look at what function has guts to it. Okay, so this is going to be a case where I'm going to use 2 u-substitutions. Now remember, the name u-substitution is just a tool of transforming an integral. It doesn't mean we even have to use a letter u. But in this case, I am going to use a letter u. Let u equal sine x, and du is cosine x. I took cotangent and wrote that as cosine and sine. And I do see a cosine times a dx there. But I have this little pesky sign right there in the denominator, so my integrand becomes natural log of u over u du. Now this integral can be determined with another substitution. So I noticed that if I took the derivative of natural log of u with respect to u, that would be 1 over u. So let's do another substitution. So let v equal natural log of u. And by the chain rule, natural dv is 1 over u du. And we see a 1 over u du right here. So that's a dv. And we have and natural log of v u is equal to v. So we end up with just this integral, which we integrate by the power rule and get 1/2 v squared plus a constant. We can substitute in what v is, and then I can substitute in what u is, and I get this result. And so again, what I want to do in Desmos is just verify that it is the actual result. So I'm going to first write down our antiderivative we found. We have 1/2 the quantity of natural log of sine of x squared. And we're trying to verify if that equals a cotangent x natural log of sine x. So cotangent of x natural log. You see they're right on top of each other, which means this function is the antiderivative of that function. So you can see that sometimes you can do multiple u-substitutions, and that can help you find the final result. So get started on the homework, ask questions to remind, and I'll be posting another video about chapter 7 as we get into applications of integration.